Welcome to kinointernet.com. Please like, share and subscribe my videos. Today we're going to look at the directing effect of the existing group on the benzene ring. If you look at the benzene ring normally undergoes the electrophilic addition, and they always try to keep their delocalization. The hydroxyl group, which is the existing group, is going to decide whether the oncoming group is going to actually come at 2, 3 or 4. We can call it, this is 2 and this is 3 as well. These positions are the same. We also call number 2 position as ortho, so we call it as 2 ortho position. And a benzene, you always have 2 meta position, which is 3, and para means parallel, and 1 para position. Now based on that, we normally use this delocalization benzene ring, but to understand how this works, I am going to use the Kekulé structure to explain the activity of benzene based on the existing group. Now if I will actually look at the oncoming electrophile, a benzene has got so much electron density, high electron density. It is not an alkene, but it has some sort of the pi bonding. So in that case, it will actually undergo the electrophilic addition. If this group is going to approach the benzene ring will actually allow it to actually go on to any of the positions. But we will see how this hydroxyl group is going to allow this NO2 group. Now to understand NO2 group, you need to understand NO2 has got a actually positive charge on it. Now we're gonna start with the delocalization, how the electron pair is actually delocalized. Now the first thing what's going to happen is if NO2 is coming and it is going to actually attach here, for example at number 2 position, this is one of the possibility. Either it's going to go at number 2, 3 or 4. These are the 3 possibilities. So let's have a look which one is more preferable in terms of reacting with the NO2 group. NO2 group is going to attack, so I would say this is benzene ring. So obviously the delocalization will be distorted, so I will put NO2 there and I put hydrogen there. Obviously each carbon atom is attached with 1 hydrogen. Now what's going to happen after the delocalization will happen, and you do not know where the actual position of these 2 electron pairs. So this will carry positive charge, so this will move on this side, and that will actually make a double bond there, and that stays there. So this double bond stays as it is. This double bond moves of 1 position backward. So please do remember, when you do the directing effect, or when you actually explain the bonding in terms of the existing group, the double bond, when it will be delocalized, it will go 1 position backward. Once it's done, the positive charge will jump 2 positions. Because this electron pair is donated to NO2, that's why positive charge will appear onto this carbon atom, and that carbon atom has got 4 bonds. So the positive charge will jump 2 positions. It will come here. You can also calculate this carbon atom has got 1, 2, and the third is a hydrogen bond, and if 1 bond is missing, so that's why it will carry positive charge. NO2 will remain as the same, and hydrogen there, and we're going to look at what's going to happen next. Because it has this electron pair there, so it will move 1 position backward, and then you will have the positive charge will appear there, right underneath the OH group. Once it's done, OH actually contains electron pair. Obviously not all the atoms contains that. You will see that because of that, this electron pair normally after this it cannot go further, because this positive charge like this should have a double bond on the next second carbon atoms after this, but after this this here there's no double bond, so it should stop. So in this case no double bond will be coming to rescue this positive charge inside the benzene ring. Now look at the OH group. OH group will suddenly realize that there is a deficiency of electron inside the benzene ring, so it will actually donate its electron pair between the carbon atom and the oxygen, and that will actually produce a double bond between this carbon atom and hydrogen to make 4 bonds. Now if you look at carefully, all of the carbon inside the benzene ring all have 4 bonds now. But this oxygen whenever it makes 3 bonds, it will always carry positive charge, just like nitrogen. When it makes 4 bonds, it carry positive charge, like in NO2 group. Now after this, that's it. That's the maximum you can go for delocalized structure. Now these are called delocalized structures of benzene ring. We can have a look again. So we have 1, 2, 3, 4 different structures, and now we're going to look at another possibility. So we are not actually saying what is going to happen. We are looking for a possibility that the NO2 group will attack at number 3 position. In this case, the benzene ring will actually lose its positive charge there, and then you have NO2 there and hydrogen there. The only reason I'm doing this, just to make sure, it doesn't matter where you're going to draw these double bonds. I could have drawn the double bond there, but it doesn't matter at all. So after this, this double bond will actually go there to make sure that there will be no positive charge there, and it will be delocalized that side. NO2 stays as it is. Positive charge will appear 2 positions away from it. After this, this double bond will delocalize there. This is a problem. Now we're going to look at the third position, which is number 3 there. If NO2 is going to attack on this carbon atom, you will see that this will carry NO2 and hydrogen. Because NO2 is an electrophile, this will appear. Now what's going to happen? Obviously positive charge will appear on the carbon atom next where the NO2 is actually attached. So this will come back there, and that will actually produce a double bond there, and positive charge will appear there. NO2 and hydrogen. After that, you will see that you have hydroxyl group there as it is. You have NO2 group as it is, and then you have hydrogen there. Now what's going to happen is this double bond obviously go back in the on that position. So that means once it's going to go there, the positive charge disappear and double bond will appear there, and positive charge will jump to 2 positions from there to there. Now after this, there is no double bond available. There is no lone pair of electron can be offered at the moment. You must be thinking nitrogen has actually a lone pair always, but at the moment it doesn't actually have it, because nitrogen belongs to the 5th group and oxygen belongs to the 6th group. Oxygen is more electronegative. Even nitrogen try to donate that electron pair, it's not going to happen, because oxygen will pull the electron density towards itself, and nitrogen will actually not going to offer any electron pair inside the benzene ring. So only 3 possible delocalized structures. In chemistry, we call them as resonance, the possible structure based on delocalization. We call them as resonance structures. So in ortho position or in number 2 position, we will have 4 possible structures. In number 3, which is meta, we will have only 3 possible structures. In the same case, if you have benzene ring, and NO2 is going to attack on to this side, will attack on this side, so obviously the arrow will go from benzene to NO2 because NO2 is electron deficient. In this case, that double bond will disappear, not this one, because that has got nothing to do with this carbon atom. So in this case, this double bond will be broken and positive charge will appear there. NO2 stays as it is, OH stays as it is. Those 2 double bond will stay as it is. Now this double bond will come here to show further resonance, and the positive charge will appear there. You have NO2 there and hydrogen, and because of this is transferred there, so double bond will appear there, and this double bond stays as it is. After this, you will look at it that there is a possibility, rather going forward, the oxygen will start feeling what is going on. So it's going to actually start donating its electron pair. Oxygen can donate the electron pair because oxygen is actually attached to hydrogen, which is less electronegative, so it has no problem of donating that electron pair to this carbon atom. So in this case, the arrow will go from there to there, and you will see that the double bond will be produced. Everything remains the same. You will see each carbon atom, if you count it, has got 4 bonds now, no problem of positive charge. But oxygen has got 3 bonds now, so it will have actually 3 bonds and positive charge. Now after this carbon atom, these 2 carbon atoms which has got double bond, that can further delocalize. So oxygen will take the electron density. And the reason why is going to happen because the alkyl groups always are in electron donating in nature. So the oxygen will take its electron pair back, and then this one will appear there, and that stays there. Positive charge will appear right there. Now, obviously, based on this, you can see that the positive charge jump from 1 to, and that it will appear next to the carbon at NO2 group like in this one. Now, this is the 4th structure. So you have 1, 2, 3, 4 structures. Now, when you do the chemical reaction, you must be thinking, if these are the 3 possibilities, you should get 3 products. Yes, you should get 3 products. The problem we have is that the most resonance structure, the more stable your intermediate is, and then you will get more product. That's the law in chemistry. Now based on that, if you look at these two, which is ortho and para, or 2 and 4 position, they both are producing 4 resonance structures: 1, 2, 3, 4, 1, 2, 3, 4. 2 laws in chemistry. Number 1, the major product will be the one which actually produce more resonance structures. Okay. Second, the one which actually has got a stable carbocation, and I'm going to come to that in a minute. So based on that, if you look at it, these 4 are going to be the major product. Now if you do a chemical reaction of nitro group, you probably will get OH stays there, and you will get NO2 plus you will get another product, OH, NO2. This one gonna be 67%, and this is gonna be probably 32%, and you might will get a small amount of 3-nitrophenol, 1%, and that is because of the delocalization being shown in the other structures. Now you must be thinking that if they both have produced the same number of resonance structures, then why there is a difference of concentration in the product? The answer is there are two ortho positions. So you can see each benzene ring or the derivative of benzenes where you have existing group already, you have two ortho position or two positions, whereas you have only one 4 position. So that's why it will produce a double product as compared to the para product or number 4 carbon product. And this is one of the very least amount, maybe 1% or 1% will appear in the solution. Now, if I talk about the second part, which is what if you have CH3? If you have CH3 there, CH3 are actually electron donating in nature, but they're not going to participate in the electron delocalization while resonance structures are made, because they do not have electron pair. So you cannot donate an electron pair. So all you have to do is you replace this with CH3, and I'm going to come to that in a minute, that how this is going to happen. I'm just going to replace all of them, and I'm going to explain them one by one. And I will remove the one which is not required. Now, even you have CH3, you still be looking for an electrophilic substitution or benzene ring. Now CH3, everything is going to be same thing, everything happening up to here and there. After this, you cannot have this structure, because this structure is produced because of the OH has actually donated the electron pair. So the maximum possibility is that you have 3 resonance structures when you have a CH3 group or a group which cannot offer an electron density. So that's the maximum possibility of making resonance structures. If you are attacking at number 3, you're producing NO2 and hydrogen, and you will see it will carry on and everything will remain the same, no problem. For the para group or number 4 group, you will see that the nitro group is there. Everything is same except one thing, which is the last bit, which is here. You can't have the double bond there, so what's going to happen is this structure will be eliminated. Because after this, this one will go there, and double bond will produce there and positive charge, and it will stop because there is no double bond on this second carbon atom which can be offered to this positive charge. So 3 possibilities. Now the law was whoever is going to make the major product, whoever is going to make more resonance structures will be the major product. And in this case, all 3 of them, the 3 possibilities in the benzene ring due to existing group, there are 3 resonance structures in each case. Now we use another technique to predict which one will be the major product. And the technique is that whichever is going to produce a stable carbocation. Now stable carbocations are produced, we will look at whenever the carbon, so tertiary carbocation is more stable than the secondary carbocation, which is more stable than the primary carbocation. When carbon which carry positive charge is attached with the 3 carbon atoms, it is known as tertiary carbon atom. Let me give you a tip. When you deal with the benzene, you always have actually secondary carbocation in all cases. There is only one case when you're going to get the tertiary carbocation in the system, when you actually have an alkyl group as an existing group. Let's have a look. Look at this carbon atom. This carbon atom, whenever the charge will appear there somewhere like this carbon atom there will have 3 carbons attached to it. 1, 2 and 3. So this one will produce. So when the NO2 group is going to attack number 2, it is producing a stable carbocation, which is 3C plus. In terms of 3, when NO2 is going to attack a number 3 position, you can see that the positive charge did not appear under CH3. You can see that under CH3 it didn't appear, so there is no tertiary carbocation. It does have actually secondary carbocation, so still it is less stable than the tertiary carbocation. Now look at the third one. If you look at it, I've just spotted 1, 2, 3, so this also produce tertiary carbocation. Let me give you a tip: 2 and 4 position. 2 and 4 position always appears at the same time. It's just the difference between the concentration, because one has got 2 positions and one only have 1 position. That's why the concentration of number 2 position always double than the para position. Now, based on that, if you look at it, the major product will be 2 and 4. 2 and 4 nitro aniline will be the major product. Okay. Now, these are the ones which are called electron donating group. So if you have the electron donating group on the benzene ring, you will always have 2 and 4 product. What if you have something which is actually electron withdrawing group? In that case, obviously, you are not going to have the position at or 2 or 4. So we're just gonna quickly have a look at that as well. If you look at the any group which is NH2 is actually electron donating group, but if I put NO2 there, then it's going to be an electron withdrawing group. This is electron withdrawing group, and you can have an electrophile. We're not going to have we just put E there just to make sure that we do not use the same. So this electrophile will be replaced. 3 possibilities we have: either it's going to go on to the 2 position, or 4, or 3. So we will look at all 3 possibilities. We have to replace obviously this one by NO2. I will actually explain that in a minute, why NO2 is actually electron withdrawing, why NH2 is actually electron donating group. I did say that earlier, but I'm just going to explain that again. Now have a look onto this one. NO2 group, nitrogen is attached with oxygen, so oxygen is actually more electronegative. That's why the electron pair on nitrogen cannot be further delocalized inside the benzene ring. Whereas when you have NH2 group can donate the electron pair inside the benzene ring, because N is attached with the hydrogen next to it. So the shortcut is to remember, whichever atom attached directly to the benzene ring, when it is attached to another atom which is more electronegative, it will withdraw the electron density. It will take the electron density out and deactivates the ring. The moment it's going to deactivate the ring, the electrophile will not actually go on to those positions where you have a positive charge appear. So now we're going to have a look now the possibilities. Now if NO2 group is there, we will have what do you call it as first possibility at number 2 position. Everything remains the same. You will have a E there, all of them will appear there. The moment you're gonna come here, that's the end of it. But one more thing is gonna happen is the NO2 group carry partial positive charge because oxygen is more electronegative. Everything remains the same. You can see that all are same, so it's going to carry on, and same goes for NO2 there. Everything is same for here. Everything is same, and the only thing I'm going to highlight is that this carbon atom, which actually carry positive charge now, will have the partial positive charge on nitrogen. Now, two laws. Number one, the major product will be which has more resonance structures. In this case, all three structures are same for each position. So, three possible resonance structures for 2, 3, and 4. So, we can't apply that law. Second law is stable carbocation. Now, in this case, we do not have a CH3 group or carbon on the top of the benzene ring, so we do not have any distinguished carbocation which can actually decide the major product. Now, the third thing which we can use actually, whenever you see two positive charges coming close to each other, that product will be less stable, or that intermediate will be less stable. Your intermediate either based on carbocation, or it is based on the what sort of environment it has around it. Now, if you look at this positive charge there, because it appears right under NO2, nitrogen carry positive charge, and this carbon carry positive charge as well. This nitrogen can also be C double bond O, an ester group, or an aldehyde, or a ketone, any of these groups. What's going to happen is, because it has partial positive charge and this one has partial full positive charge, they will oppose each other. The moment the structure is going to appear, it is not going to stay in the solution, so it just disappears straight away. So the life of the intermediate is very small in this case, because according to physics law, same charges repel each other. I'm going to repeat that again. Because both has same charges, so this intermediate is not going to actually be stable, and they will actually repel each other straight away, and because of this, this structure will not be the exact possible product. The third one, you will see positive charge appears right under the nitrogen, which is carrying positive charge, so this is also not stable. The last bit is actually the benzene ring, where you can see that the positive charge actually did not appear right under nitrogen. So basically, this one is the most stable product based on the most stable intermediate. So the whenever you have, sorry, I'm going to replace this NO with NO2. Whenever you have an electron withdrawing group, and how you predict it, the existing atom is attached with any other atom which is more electronegative, it is then these groups can actually withdraw the electron density out of the benzene. And there is a mechanism about that as well. I can draw that, and I can show you how oxygen withdraw the electron density. So the nitrogen group is delocalized, it's been taken by one of the oxygen, and oxygen will withdraw the electron density, and it is the main cause. So in this case, number 3 position, or meta position, is major product. And this is basically how you actually explain the acting effect. Thank you very much.